So today we are going to start the leaving group. So leaving group means the species which leaves in a chemical reaction. The species which leaves in a chemical equation or chemical reaction. This is the sign of reaction, okay? For example, suppose we have a hydrocarbon bonded to a leaving group and we are going to break this bond. So it would be R plus leaving group minus. This arrow is very important. The head of arrow indicates negative charge, tail of arrow indicates positive charge. That's why once you are going to break this bond, the R part have a tail of arrow. It definitely starts from the middle of the bond, but it means it is a part of R. So R have positive and Lg means negative. Lg stands for leaving group. Generally, weak bases are good leaving group. And weak base means strong acid because strong acids are weak base. And we have learned in acid base chapter how to compare the acidic strength of a given organic compound. Suppose you have HF, HCl, HBr and HI. And we have to compare the acidic strength of these acids. So first of all, you have to make its conjugate base, which means F minus Cl minus Br minus iodine minus. Now you know that if you're moving top to bottom, size increases. And the stability of anion, this anion is more stable because in bigger size, we have less charge. So that's why iodine stability is greater than the Br minus, than Cl minus, than F minus. So this is the acidic strength order. The conjugate base, this is the conjugate base. And this is the stability of conjugate base as well. So more stable conjugate base is stronger the acid. Okay. So if you have a strong acid, that means weak base and that are good leaving group. So if you compare between fluorine, chlorine, bromine and iodine, which one is a good leaving group? So we can say the trend would be the leaving group would be best iodine minus, then Br minus, then Cl minus, then F minus. It makes sense about this order. Suppose we have two bond Ri and Rbr and RCl and Rf. So the best leaving group would be iodine. Means if I am going to arrange in the bond strength, suppose I am saying which bond is a stronger bond, which one is a weaker bond. So iodine carbon bond is the weakest bond. This is the weakest one. So if it is weakest, it means it can break and R plus will form. So R plus would form faster in amount than Br, Cl and F. And this bond is the strongest bond. So strongest means bad leaving group. Bad leaving group. It makes sense? Tell me everyone. Perfect. Okay, now second thing, if you have OH minus and H2O, and I said that leaving group means weak base means strong acid, and you know that if you want to compare between OH minus and H2O, H2O is a strong acid because if you apply cardio, you know that the first thing is charge. Charge means the neutral is the means positive charge is the most acidic, then neutral, then negatively charged. So if you compare between negative and neutral one is a more acidic. That means H2O is a weak base, so it is a good leaving group. Makes sense? H2O is a good leaving group. Please tell me everyone. It makes sense. Which one is the best leaving group? Okay. Some leaving groups are very common one like N2. N2 is the best leaving group. Best leaving group. So one more thing I would like to teach you here. Suppose we have OH and we want to break this bond. So this breaking is wrong one, R plus OH minus. This is the wrong breaking. Because OH is not a good leaving group, bad leaving group. So we have to make OH as a better leaving group. So we will protonate first. Means we will react with the OH with the H plus. No worry, no worry. So OH is going to protonate with the H plus. So it means it is my protonated alcohol. And you know that now it is the best leaving group. So it can break and it will form R plus and H2O. So this is the best way to generate the carbocation from alcohol. So do not break the alcohol bond directly. First protonate because now it is a good leaving group. Good leaving group. Make sense? Okay, perfect. Some important leaving groups you should know, like the name of those. So the very first one is this one. This is called tosylate. Tosylate. So tosylate in short we can represent as OTS. So this is a good leaving group. So whenever you have any chemical reaction, suppose R here OTS, so you can eliminate OTS very easily because it is a good leaving group. The second is this is called nosylate. Nosylate ONS. This is also a very good leaving group. Here I am writing a best leaving group, important leaving group. So tosylate, nosylate, these are very good leaving groups. And this is also triplet. This is called triplet. Clear? So generally these three are the best one. There are some more, but these three are the very important one. Tosylate, nosylate, triplet. And I also told you the best way to figure out the leaving group is generally water is the best leaving group. Generally N2 is the best leaving group. Tosylate, nosylate, triplet is the best leaving group. You know, stable anion is the best leaving group. Stable anion. And we know that stable anion means strong acid. Strong acids are weak bases. So sometimes these terms can also help you. So weak base are good leaving group, or strong acid are good leaving group, or stable anion is a good leaving group. Okay. Now the next is suppose you have ether. And this is not a good leaving group. So you cannot break this bond like this. So you can form R plus and OR minus. This is wrong approach. Because this is not a good leaving group, OR part of the ether. So we will protonate this first. We will protonate, like we can react with any acid or any proton. So now alcohol protonated. So now we can break this bond and it would be R plus plus ROH. So this is now good leaving group. Make sense? So it will help you in a chemical reaction like in chapter ether. Any doubt about this ether one? This one is also very important. This is amine. So when amine is treated with NaNO2 with HCl, or it reacts and it forms HNO2, nitrous acid. Nitrous acid. And when amine is going to react with nitrous acid, it forms RN2 plus. Now N2 is a very good leaving group. So it forms R plus plus N2. So simply you cannot break amine bond in this way to form R plus and NH2 minus. This is the wrong approach, okay? So first you can generate N2 plus from amine, and then it can be a good leaving group. This is a good leaving group. And then you can form a carbocation. Make sense? Please tell me, everyone. Okay. So next is potential energy diagram. In potential energy diagram, generally we have two kind of reaction. Single step and multiple step. Suppose we have single step reaction. So reactant is going to convert into product. And here we have a transition state. TS means transition state. So this reaction can be exo or endo. Whenever the reactant energy is higher than the product, like this is the reactant, this one is my product, this one is a potential energy, this one is a progress of reaction, and this peak point is known as transition state, TS. This is a single step reaction because we have just one peak. And this graph is exothermic. This is exothermic. Why exo? Exo is like out. Which part is out? Reactant. It is outer than the product. The energy of the reactant is higher than the product. So the delta H for exothermic is negative. Make sense about this graph? Now look at this one. Reactant, product, transition state, potential energy, progress of reaction, and this is reactant is inside than the product. So this is endothermic. Endo means inside. So reactant you can see is lower than the product. And this delta H would be positive. So single step reaction always have a single peak. Make sense? Now multiple step. Let's talk about double step, means two-step reaction. So reactant, it would form first intermediate, then intermediate is going to form product. So here we have transition state first from reactant to intermediate, then intermediate to product would be transition state 2. Clear? So let me know how many peaks in the two-step reaction. How many peaks? Very good. So it could be like this. Anyone can be bigger or smaller. It's just an example, okay? So this is my potential energy. This one is a progress of reaction. And this is transition state first. This one is a transition state second. And the lower one, this one is called intermediate. This is intermediate. This is my reactant. This one is my product. Make sense? The highest peak would be my slow step. This is my slow one. And this one is my fast step. So this is the slow one. And in any chemical reaction, slow step is called rate determining step, RDS. So this is my RDS step. Clear? Please tell me, everyone. And reactant to transition state, this energy gap is called activation energy. And this one is also activation, this. Okay. So here a question can be, this is supposed to be my first step, this is second step. Now let me know what is the nature of second step. Exo or endo? Tell me. Exo or endo? I'm talking about the second step. Yes, reactant energy is outer than the product if you compare. So second is my exo. And what about the first step? Very good. It's endo. Very good. Very good. Perfect. Okay, now the second example, the three-step reaction. So reactant, intermediate 1, intermediate 2, then product. This is the transition state 1. This is the transition state 2. This is the transition state 3. So reactant, product, potential energy, progress of reaction. This is intermediate 1. This is intermediate 2. This is transition state 1. This is transition state 2. This is transition state 3. Make sense? So we can say here number of transition state that is equal to the number of steps. So here we have 3 transition state. It means we have 3-step reaction. And the number of intermediate would be less than the number of transition state. You have to subtract just 1. So if transition state is supposed to be 3, then intermediate would be 2. Clear? Now suppose this is my first step. This is second. This is third. Now let me know which one is my RDS here. Which one is the RDS? Very good. Perfect. First one is RDS because high activation energy as well as the highest peak. Clear? Any doubt? Perfect. So reactant whenever converted into product, so you have intermediate, and generally intermediate in your syllabus is carbocation, carbanion and free radical. This is called carbocation. This is called carbanion. And this one is known as free radical. And out of these three, the carbocation is the most important one because there is a property of a carbocation which is called rearrangement. Okay. So this is an important factor for carbocation. That's why this intermediate is so important. So now we are going to discuss carbocation rearrangement. But before moving to the rearrangement step, I would like to ask about the stability. Do you have a very clear idea about this stability? Please tell me everyone. Do you know the stability of carbocation? Okay, let me give you a question. Yeah, everybody know about the tertiary, secondary and primary. This is the very basic one. Believe me, this is a very basic information. But that is not good enough for the DAT. Generally, booster and boot camp have only this, in the stability of carbocation and rearrangement, but that is not good enough. So the reason is that, let me tell you the reasoning behind this. Suppose you are familiar with this example. You are familiar with this example. This is the tertiary one. This is the secondary one. And this is the primary one. So you can say this is tertiary, this is secondary, this is primary. So tertiary is most, then secondary, then primary. Am I right? This is tertiary because the carbon is bonded with the 3 carbon. So whenever carbon is bonded with the 3 carbon, that is called tertiary. When the carbon is bonded with 2, that is secondary. When bonded with 1, so primary. Now let me know about this one. Which one is a more stable carbocation between 1 and 2? They both are secondary. They both are secondary. Tell me. That's why I am saying do not memorize. Do not memorize. No, first is not. First is not. Let me tell you the reasoning behind this. Then you will be able to answer this question without any help. Without any help. No, we will talk about rearrangement later. First, we are going to discuss the stability. So my question is stability here. Let me tell you the reasoning behind this. Look at here. There is an effect called hyperconjugation. Let me tell you why tertiary is the most stable than secondary than primary. And there is a one more methyl carbocation. 1, 2, 3, 4. Okay, listen me very carefully. The carbocation neighboring carbon, the direct carbon, the very first direct carbon is called alpha carbon. So this is alpha, this one is alpha, this one is alpha. And the hydrogen bonded to the alpha carbon is called alpha hydrogen. So let me know how many alpha hydrogen in the compound 1. 9. 3, 3, 6, 3, 9. So alpha H is 9. We have to count all the hydrogens of alpha carbon. And what is alpha carbon? Adjacent carbon bonded to carbocation. Okay, what about the second one? How many alpha H? Alpha H. I am not saying alpha carbon. I am saying alpha H. 6. Very good. How many alpha in the third one? Very good. And how many alpha in the fourth one? 0. Because there is no alpha carbon. So stability of carbocation directly proportional to number of alpha hydrogen. Simple. No need to memorize tertiary, secondary or primary because some of the cases, suppose my both carbocation are secondary or tertiary. So it's better to figure out the alpha H. So that's why this one is the most stable than this, than this. Clear? How many alpha H here? Whenever you have a bond line structure, always try to convert in the expandable form. Means you have to put hydrogens on the neighboring carbon. So first of all, we have to find out the alpha carbon here. So this is my carbocation and we have to find out the direct carbon bonded to the carbocation. So this one is my alpha, this one is my alpha and this one is my alpha. So if you are going to put the hydrogens over this, so we have 2. Here we have just 1 and here we have 3. So how many total? 6. Please tell me everyone, make sense? Okay, what about here? How many alpha H? Yes, this one is alpha. This one is alpha. This one is alpha. So 3, 2, 1. So 3, 2, 5, 1, 6. Whenever you have a double bond, suppose in the neighboring position, suppose here, there is a double bond. This is definitely alpha. This one is also alpha. Do not count the hydrogens of double bond. Clear? Always count the saturated, means single bonded alpha. So how many alpha H here? Only 2, because we will calculate only this part left. Make sense? Okay, now answer this question. More stable carbocation. Yes, how many alpha H in the first one? How many alpha H in the first one? 4, very good. How many alpha H in the second one? 5, very good. Now it makes sense. So try to be smart. Do not like follow the memory based things, tertiary, secondary, primary. No. If you are going to explain something, it means you have an idea about that kind of thing. Clear? So whenever a question is about stability of carbocation without resonance, then alpha H. Simple. Okay. Now second thing. Whenever you have a question from stability of carbocation, the first preference is given to resonance. Resonance dominates over all the effect. And then second, hyperconjugation. Hyperconjugation. Hyperconjugation means alpha H. So let's discuss some example. So here we have 4 carbocation and we have to arrange in the decreasing order of stability. So I said that first apply resonance, then alpha H. So first we will figure out the resonance in the given carbocation, and I have discussed resonance a lot in my videos. So first one have resonance. Any doubt? Please tell me everyone. Compound 1 have resonance. Compound 2 also have resonance. Make sense? Please tell me. Okay, perfect. There is no resonance in the third. There is no resonance in the fourth. So one thing is very clear. First and second have higher stability than third and fourth. Okay, now find out the alpha H. How many alpha H in the first one? And I said that do not count the double bond hydrogen. How many alpha H? 3, 2, 5. How many alpha H in the second? Only and only 1. How many alpha H in this third one? 7. And how many alpha H in the fourth? 4. So resonance with higher alpha is compound 1. Resonance, definitely it has lower alpha H, but we have resonance and resonance higher than the hyperconjugation. So second, now between third and fourth, only hyperconjugation. So third and then fourth. Make sense? Okay. I have a question, and there is definitely one question in your exam about the carbocation stability. Every time you have a one question from the stability of a carbocation or free radical. Arrange them in decreasing order of stability. Okay, compound 1, resonance, yes or no? Compound 2, resonance, yes or no? Compound 3, 4, and 5, I think no resonance. How many alpha H in the first one? 0, very good. How many alpha H in the second one? 0, very good. How many alpha H in the third one? 4, very good. How many alpha H in the fourth one? Fourth, how many alpha H? 3, 3, 6, 2, 8. How many alpha H in the last one? Only one, this. So now compound 1 and 2, it's identical. You can see they have the resonance and they have just one alpha H. So 1 and 2 have equal stability. Now between third, fourth, and fifth, they don't have resonance. So it's quite easy for you. So fourth, then third, then fifth. Make sense? Tell me, everyone. Perfect. Now next is rearrangement. Rearrangement is basically less stable form to more stable form. Less stable to more stable. And it always occurs at neighboring position, like 1-2 position. Rearrangement is always 1-2 position. For example, suppose we have this carbocation at this moment. Right now we have just 3 alpha H. If we are going to shift positive charge over here and one of the hydrogen is going back to this carbon, so the new formed carbocation would be CH2 plus CH3, and you can see again 3 alpha H. So they don't have change in stability, they have equal stability, so no rearrangement. Make sense this example? Because we have stability equal. Now second example, how many alpha H over here? Just one. So if you are going to keep this hydrogen, we are going to shift hydride here. So hydrogen is going back to this carbon. So how many alpha H? 9. So stability increases. It means it would rearrange, and this kind of rearrangement is known as 1,2 hydride shift. Clear? This is called 1,2 hydride shift. Make sense? You can say like why methyl is not going to shift here. If you are going to shift methyl, suppose we are going to shift methyl. Now this CH2 is bonded to CH3. How many alpha H here? Tell me. This is alpha, 3 to 5. And how many alpha H here? At this moment, 1. So if you compare by the hydride shift, my alpha hydrogen is 9, but methyl shift produces 5. So hydride shift would be faster than the methyl because we have higher stability by the hydride shift. So methyl shift would not be possible for this. Make sense? So simple thing is that we have to produce most stable carbocation by shifting of atoms. It can be hydride, it can be methyl, or it can be any other group. But the thing is, we have to make a most stable carbocation. Any doubt? Tell me everyone, it makes sense?
So hydride would always produce more
This is not hard
hydrogen.
and fast rule. It's experimental. So if
Okay.
you have a carbocation, you can check. You can check by hydride or you can check by methyl. But the
Mm-hmm.
migratory aptitude of hydride is faster than the methyl.
Okay.
Yeah.
Got it.
If you have methyl and hydride, you can shift your hydride first. Okay.
Okay.
If you don't have a hydrogen, then you can go with the methyl or any other atom. Let's talk
Okay.
about
Thank you.
1, 2 methyl shift. It always like the high. Yeah, whenever hydrogen is present, you can go with the hydride shift. Especially for the DAT. I'm not talking about more than like Orgo 2 or Orgo 3 like that. It's just a DAT standard. Hydride is good enough. Now here, alpha H is just 0 and this is primary carbocation. So you can shift one of the methyl group. Why this is 1, 2 shifting? Because this is 1, this is 2, okay? So if you are going to form a new carbocation, so how many alpha H? 3, 3, 6, 2, 8. So stability increases. This is called 1, 2 methyl shift. Make sense? Please tell me everyone. And now the next is 1, 2 phenyl shift. Phenyl is called benzene type of compound. Suppose we have this one. We can represent through pH. Oh, sorry, this is. So one of the pH is going to move here. This is CH2 pH. This stability increases not because of this is, you can see alpha H is 0 here, and here we have 2 alpha H. Or also you can see there is no resonance here at this moment, no resonance. But here we have resonance. You can see this carbocation is in the resonance with the benzene ring. If you are going to draw this structure, another ring, and then CH2PH. Makes sense? So you can see this positive is a part of ring here, which is in resonance. So resonance means stability increases. So this is called 1, 2 phenyl shift. Make sense? Please tell me everyone, it makes sense? And the rearrangement is very, very important. Like in SN1 reaction, in E1 reaction. Why? Because they have a carbocation as an intermediate. Now the next is ring. there is a ring rearrangement. So we have two categories in the ring rearrangement, ring expansion and ring contraction. What is ring expansion? The condition, listen me, the stability of ring is 6-member, then 5-member, then 4-member ring. So the condition for ring expansion is, if you have a 4-member ring, 4 could become 5. And if you have a 5-member ring, it can become 6. Generally, these two cases are the most common one. Okay. So it would be 4 to 5 and 5 to 6. What is the condition here? So ring outer carbon must be positively charged. Ring outer carbon, the very first carbon which is bonded to the ring, that should have a positive charge. Then the ring expansion can take place. Like here, we have a 4-member ring and we have a carbocation in the outer carbon. So here we have a ring expansion concept. And you know that 4-member ring could be 5-member. So what is the best way to draw the ring expansion? So listen me here. You have two things. You can draw with arrow pushing or you can draw with the numbering rule. So let me tell you the first arrow one. So you can break either this bond or this bond. Any one. So suppose we are going to shift this one to this carbon like here. So you know that this is positively charged. This is positively charged. So it means this carbon should be negative. This carbon should be negative. Then there is an attraction like this. Look at the concept here. So if you are going to attach this bond with this carbon, it means it should be negative and it should be positive. Make sense? Please tell me this breaking makes sense. And you know that opposite charges have attraction. So this plus is going to bond with this negative. So now you can see if you count the number of carbon in the ring. So 1, 2, 3, 4, 5. So you can draw 5-member ring. And you have a positive charge here. So keep positive on any of the carbon here positive. Make sense? Or even you can do one more thing. Suppose this one. So you can do numbering here. Suppose this is my 1, this is my 2, this is my 3, or this is 4. Wait, only you can number 1, 2, 3 only. That is good enough. Either this side or this side. So the simple thing is that connect to 1, 2, 3. We have to connect to 1 and 3 and keep positive at number 2. Keep positive at number 2. Number 2. So you know that 4-member ring would be 5. Now you can numbering here. This is my 1. You know that 1 is bonded to 3. So this is 3. And now 1 is bonded with a carbon which is supposed to be 2 here. So I said that keep 2 as a positive charge. And now you know that one carbon has an outer side carbon, so branch. Make sense? So this is called ring expansion. Okay, would you like to try this one? What would be the ring expansion of this? You have, you can directly send the picture on my messenger. Yeah, you can send me the picture. Six-member, I know that 5 would become 6, but what would be the right connectivity? So please send me the picture. I told you the basic concept. Either you can break this bond and attach to this, or you can do numbering 1, 2, 3. So you know that 5-member ring would be 6. And keep number 1 at any carbon. It's your choice. I got one answer and it's correct. Suppose any carbon has 1. Suppose this is my 1. Now 1 bonded to 3 and 1 is also connected with the 2. So 2. Now you know that keep number 2 as positive and 1 has outer side carbon, which is methyl. Make sense? Please tell me. It makes sense? Okay. Is it the most stable carbocation or still we have some rearrangement like hydride, methyl? Is it the most stable form? Tell me. Is it the most stable form? No, yes. We have a hydride here. And right now we have how many alpha H? 3. So if you are going to shift your positive over here, so it would be this one. And alpha H is here 3 to 5 to 7. So this is the most stable form. This is called 1, 2 hydride shift. So finally we have this one as a carbocation. This is the ring expansion. Make sense? Any doubt? Okay, what is the use of this kind of thing? Suppose we are learning SN1 reaction. SN1 reaction we have. It's a just example. Don't worry what is SN1. Let's start this. Suppose we have this one as a compound, chlorine here. And here we have a nucleophile, suppose OH minus. Okay. So generally in SN1 reaction, the carbon halogen bond is going to break. So this is going to break and it forms a carbocation. Now we have learned whenever you have an intermediate as a carbocation, always check the stability and rearrangement. Always check the basically rearrangement. Always check the rearrangement. If you have ring, then you can go with ring expansion. If you have a 5-member ring, then it can go with the 6. If you have 4-member ring, then it would be 5-member ring. If you have a 6-member ring, then there is no ring expansion. It makes sense what I'm trying to say? So this is a 5-member ring. So I would like to go with the ring expansion here. And this is the condition of ring expansion. Why? Because we have a positive charge at the outer carbon of the ring. So you know that it would be 1, 2, and 3. So we have a 6-member ring. 1, this is 3, this is 2. Keep 2 as a positive and number 1 has a branch. Make sense? Now in the next step, 1, 2 hydride shift. 1, 2 hydride shift. So it would be this. And now this is the most stable carbocation. And in the next step, nucleophile is going to attach here. So we have this one as a final product, OH. And your options would be, in your options, one of the option would be this, one of the option would be this, one of the option would be this, and one it could be supposed to be this one. There is a hydride shift to make it more stable carbocation at tertiary in the ring 1. So these are the 4 options and you guys can confuse here. Make sense what I'm trying to say? And these are all the very basic thing about the reaction mechanism. Clear? Ring contraction is not in your syllabus. So I'm going to skip this one. Okay. So only you have to think about ring expansion. So what's the final product? This one is the final product. This 6-member ring with the OH. Because we have the most stable carbocation here. Clear? It makes sense? Please tell me everyone. Okay, perfect. Okay. In this case, there will not be any methyl shift. Why you are going to do methyl shift here? Because we have hydrogen over here. This is the hydrogen where we have a hydrogen over here. So suppose you are going to do a methyl shift. Let's do this. So here I'm going to be methyl and here you have a positive charge. Now it's the same as this, you can see. So after methyl shifts, it's the same. Means number of alpha H here 3, number of alpha H here 3. That's why there is no methyl shift. We have a hydrogen, so you can go with the hydride shift. Make sense? Okay, what about here? Let me know rearrangement takes place, yes or no. If there is a rearrangement, then which atom is going to shift? Hydride, methyl, or phenyl? Yes, hydride. So the newly formed carbocation would be this one. So CH2 grabs a hydrogen, so it becomes CH3. Now this is the most stable and this is 1, 2 hydride shift. Make sense? Please tell me everyone. What about here? Rearrangement takes place, yes or no? If yes, then what would be the new formed carbocation? Okay, how many alpha H right now? 4. If you are going to shift positive charge in the neighboring atom, suppose here, how many alpha H then? 5. So it means rearrangement can take place. What is the hydride? What is the shift here? Yeah, any side. It could be either right or left. Both sides have the same number of alpha H, 5. So this is called hydride shift. Make sense? Any doubt? All done? Perfect. So we have covered most of the basic things. Now we are going to jump into reactions, so type of reaction. The very first, addition reaction. The second, substitution. Third, elimination. Fourth, rearrangement. We are going to start with the substitution reaction first. So we have to cover here nucleophilic substitution, SN. SN means N stands for nucleophilic. S means substitution. So it is of two type, SN1, SN2. Okay. So in the next session, we will start SN1 and SN2. And then elimination is of two, E1, E2. Basically SN1, SN2, and there is another reaction called SNI. I is known as intramolecular nucleophilic substitution. And here in elimination, we have another that is called E1CB reaction. E1CB means unimolecular conjugate base elimination. Okay. But in DAT, these two are the most common one. So we will cover E1 and E2, and I will discuss E1CB as well, because just one example of E1CB, and similarly in SNI as well. Okay. So first we will cover individually SN1, SN2, E1 and E2. And in the last, we will discuss how to decide the path of a chemical reaction. Like a single reactant can give SN1, SN2, E1 and E2. It means the prediction of reaction. Do you guys have any doubt about this at yet? Before moving to the SN1 and SN2, I would like to say, please revise. The solvent like polar protic, aprotic. Second, nucleophile, like the strength of nucleophile is strong and weak. And carbocation, rearrangement, and stability. So this is your homework, okay? Because everything is interconnected in the organic chemistry. If you are moving to jump into SN1 and SN2, first of all, you should be strong in these three. Did you have any question? You can turn on your mic and ask me. Any questions? Okay, my next webinar would be, I would like to cover everything very quickly now because I think at least 2 to 3, I want to do at least 2 to 3 sessions per week. Minimum 2, maximum 3. So my plan is to, another one is on Thursday or Wednesday. Which day would be good for you? Please tell me. Yeah, I think that should be good, like any day. Okay, this time would be good or night? Which time? This time? This time? Very good, perfect. So again let's do on Thursday supposed to be, yeah, because you have time to revise everything. Then we can do the next session on Thursday. Thursday or Wednesday? Please tell me the last time. Okay, let's do on Wednesday. Let's do on Wednesday. Wednesday 12:30, and we will start SN1 and SN2. Okay? Perfect. Bye everyone.